Hello coders! In today's tutorial, we will be implementing multiple point lights. So I won't actually be covering any new Vulkan technique, but this will act as a good review of some of the stuff we've done so far and how we can add on to the existing engine. With the single point light we currently have, we are doing two things. We pass the point light information within the GlobalUbo to the simple render system. We use this light information to calculate the illumination for each model object. And to render the point light, we also rely on the information within the GlobalUbo to determine the billboard object's position and color. In the case of multiple point lights, things will change only slightly. The GlobalUbo struct will now contain an array of nested point light structures. The simple render system will still use the light information from the GlobalUbo to calculate the illumination for each model object, but now we'll need to loop through each light in the array, accumulating the total light intensity. In the case of actually rendering the point lights, there are a variety of ways we could do this. We could combine rendering every light into just a single draw call, with calculating the light's index within the point light shaders by using the vertex index. This is actually a really good solution, especially if rendering a high number of point lights. But not what we're going to do in this tutorial, since I want to use push constants again. Instead, we'll just do one draw command per light, updating the push constant each time. Okay, so let's get to coding. Before we start updating the GlobalUbo with an array of lights, we don't actually have any game object representation of our existing point light. We've just been using the values of what's in the UBO. If we're going to be working with multiple lights, it will be much easier if they have game object representations. So to start, open the game object header, and below the transform component, I'm going to add a new component with struct point light component. A game object having this component will be how we signal that a game object is compatible with the point light system. All this component will contain is a single float variable called light intensity. For a point light size and position, we will use the values from the transform component rather than creating duplicate fields. Then, on the game object, add a unique pointer with type pointLight component with the default value of null pointer. We use a pointer here since we want the possibility of having a null value. For example, the floor and vase game objects aren't point lights, so they won't have this component set. Similarly, a point light object wouldn't have the model pointer set, which is how the simple render system will know how to not try rendering the point light. Following this, I'll declare a helper function called makePointLight, which can optionally take a light intensity, radius, and color values. This is just a convenience function to create a game object instance with the field set so that it is compatible with the point light system. Instead, we could just create an empty game object as before and set each of these fields ourselves. The default values here can be really whatever you want. A light intensity of 10 is probably actually a bit high. In the implementation file, copy and paste in the declaration. Don't forget to remove the static keyword, as well as the default values you provided, since default values cannot be present in both header and implementation. The implementation is exactly what you would expect. First, we create a game object and set its color. A point light size is only dictated by the radius value, which we'll store in the scale.x component. And finally, create a pointer value for the point light component using the makeUnique function. And set the component's light intensity field to the provided intensity. So now we can create point light game objects. But before actually doing so, we are going to update the GlobalUbo struct to support storing multiple point lights. In the first app implementation, I'm going to move the GlobalUbo struct definition out of here and into the frame info header. This way, if other files need access to this definition, they will be able to get it. In my frame info header, I'll paste the definition in, and above it declare a new struct called pointLight. Well, first I'll actually define a max lights constant of size 10. For each object in the scene, we need to iterate through each point light and accumulate the light's effects on the model. More point lights in the scene means more computation and slower performance. So we'll stick with a conservative limit of 10 for now. Of course, there are techniques to significantly optimize to allow for a virtually unlimited number of lights, but that's well beyond the scope of this basic implementation. So in the point light struct, we just define a position and color. I'm making both vec4s just to keep memory alignment as simple as possible. In the UBO struct, we can now remove the last two fields, replacing them with an array of point lights. Finally, add a num lights field, which keeps track of the current number of active lights, since not every scene will have exactly 10 point lights. Okay, let's move on to the point light system to add support for multiple lights now. First off, in the header, add a new void function called update. This function will be used to update the point lights array in the UBO struct with the current values of any point light game objects in the scene. Then, by the top of the implementation file, just within the namespace, I'll create a point light push constant struct. At the beginning of the video, I mentioned that there were a couple methods we could use to render point lights, each with their own pros and cons. We could render our lights by indexing into the GlobalUbo information, which has the advantage of only requiring a single draw call. However, by using push constants, it's easier to add extra information per light. The shader code will be simpler, but we require a draw call per light object. I've chosen to go with the push constant approach for this tutorial. Like with the point light struct, I'll use a vec4 position and vec4 color field, but now with the addition of a float radius field as well. We could have also added the radius field to the GlobalUbo, but it would have been unnecessary since it's not used by the simple render system's lighting calculations. Now below in the create pipeline layout function, I'll uncomment the code from before and update the push constant range size to our new struct. Just below, we also need to update the push constant range count to 1 and set info to point to the push constant range variable. Now it's time to implement the update function. The point light information will all be contained by the frame info game objects map, which needs to be copied over to the UBO point lights array. We'll use a similar pattern as how the simple render system finds what game objects to render. We iterate through each key value pair of frameinfo.game objects and then get the game object reference using the kv.second field. We then need to check if this game object is in fact a point light, which is easily accomplished by just checking if the point light pointer is null, in which case we can skip over this game object. So now that we know we are in fact working with a point light game object, it's time to copy it over to the UBO. We use the light index variable declared above the for loop to know which position of the point lights array to set, and we need to set both the position and color fields. Since the translation component is only a vec3, we need to first convert it to a vec4. I have the W component set as 1, but this doesn't actually matter as this value will just be ignored. For the color field, the W component should be set as the point light's light intensity. After copying to the UBO, we increment the light index by 1 so the next write occurs to the subsequent position in the array. And finally, outside the for loop, we need to set the UBO numLights field. Whatever the final light index value is when the for loop completes will be the number of lights within the scene. And that's it for the update function. But now we need to render multiple lights. This will be very close to how we currently render multiple game objects in the simple render system. Just like the update function, we iterate through every game object, skipping over any that does not meet the criteria for being a point light. This is of course kind of inefficient and something we'll address in a future tutorial. Next, we need to provide the point light push constant data. Within the for loop, make a local push constant variable, setting the position, color, and radius fields. In the makePointLight function, we use the scale.x component to store our radius. So that's what we need to use here to extract the radius value. And then using the vk command push constants function, we can pass this push data to the point lights pipeline. We have a whole list of fields to provide. The first being the frame info's active command buffer. Next, we've got the pipeline layout. Remember that this is just the description of the set of resources that can be accessed by the pipeline. So in this case, when we created the pipeline layout above, we have both the push constant description and descriptor set layout description, which together are basically just telling the pipeline that it will have access to the point light push constant information and the GlobalUbo information. The next field is the shader stage flag, saying make this push constant information available to both the vertex and fragment stages. Then we have an offset of 0 from our push constant struct, the size of the push constant struct, and finally the address of the push variable. The last thing to do is call the draw command for each point light object, so move that function call into the for loop from below. Okay, the point light system is complete. Now it's time to fix up our shaders. Since we've modified the GlobalUbo definition, we're going to need to update every shader file. Starting in the point light vertex shader, I'll declare the point light struct with vec4 position and color fields. Following that, add the point lights array with a size equal to whatever was the max size you declared in the frame info header. Vulkan has a concept known as specialization constants, which, as the name might imply, is a method to pass constant values into shader programs at the time of pipeline creation. So rather than hard-coding this value of 10, we could instead pass it in as a specialization constant. But since we haven't covered this topic yet, hard-coding for now should be fine. Just be aware that if you change the max light value in the frame info header, you also need to update each hard-coded value in your shaders. And finally, there's the numLights field. Now copy and paste both the UBO and point light struct definition into all 4 shader files. So we can replace the old UBO definition and now also have the point light struct being defined. Okay, starting with the simple render system, the vertex shader is fine as is and requires no more changes. But the fragment shader now needs to loop over each light to accumulate the total diffuse light contribution. So we're going to first initialize the diffuse light value with the ambient light contribution. Next, create a surface normal value. The fragment surface normal is the same for each point light, so I'm putting this here to avoid recalculating the normal each time. Then we have a for loop that iterates from 0 to numLights. We can get the point light using I to index into the UBO point lights array. Then, for each light, we need to calculate its diffuse light contribution to the total. The direction to light calculation needs to be changed to use the indexed light's position. The attenuation calculation can remain unchanged. And then to simplify the code a bit, I'll store the cosine of the angle of incidence into its own variable. So this is the same calculation as before, but we can replace the first term of the dot product with the pre-computed normal above. Next, we have the point light intensity as its color times intensity times the attenuation. Finally, we can add the intensity times the cosine of our angle to the total diffuse light value. And that's it. This iterates over each active light, calculates its light contribution, and the final output color is therefore simply given by the total diffuse light times the fragment's color. Now, navigate to the point light vertex shader. You should have already added the updated UBO and point light definitions, but we haven't defined the push constants yet. We can do this with layout push constant uniform, and then a type and variable name, which can be whatever you want. I typically just call them push. So the push constant contains 3 fields, vec4 position and color, followed by the float radius. We no longer require the light radius constant then, and that value will be provided on a per light basis. And all that's left to do is to update the position world calculation. UBO light position becomes push.position, and the light radius constant becomes push.radius. Next, copy your push constant layout and paste the definition into the point light fragment shader. Thankfully, this is also a simple change. All we need to do is change the ubo.lightColor to push.color. Now, you may think we're ready to build, and we almost are, but we haven't actually created any point light game objects yet. To keep things simple, let's first create just one. In the load game objects function of the app implementation, create a point light variable using the game objects makePointLight helper function. I'll set my light intensity to just 0.2 so it's not too bright. Then we can add the point light to the game objects map using inPlace, getting the point light's ID for the first argument, and std move on the point light variable itself. So one thing to remember is that after you move the point light variable, it is no longer valid to access it again. One thing some programmers do is that whenever they plan to create a variable to then move it, it is to limit its scope with a nested block. So this is something you may wish to do as well, but usually I don't bother. Now, the final thing to do is to call the update function we added to the point light system. We'll do this in the update section of the application render loop. Note that this function obviously needs to be called before we write to the UBO buffer. Now build and run your code and you should get a single point light object between the two vases, or wherever your origin is for your scene. Okay, but this tutorial is called multiple point lights, so let's actually get to that. I've provided a pastebin link of some rainbow light colors in the description below, which feel free to use those and paste them into the load game objects function. Then I'll create a point light game object for each color in the light colors vector. In order to set the initial position for each light object, I'm going to create a rotate transformation. This will be a 4x4 matrix created using the glm rotate utility function. The first argument is simply a 4x4 identity matrix, followed by I times 2pi all over lightcolors.size. 2pi is equivalent to 360 degrees, so what this is essentially doing is dividing a circle into equal sized slices, and then rotates each point light incrementally farther around the circumference. This will have the effect of creating a ring of lights. The final argument is the axis of rotation, which will be the up vector, and for my engine, that is 0, -1, and 0. So I'm going to make the initial translation of the point light to be the rotation matrix times the position I was using for the point light in the previous tutorial. Now, if you build and run, you should get a ring of point lights with the center of the ring at 0, -1, 0. As the final addition for this tutorial, we can actually animate the point lights as well. If we copy this rotate light matrix and navigate over to the point light system's update function, this is a good place to update the point light game object's positions. First, we can create a rotate matrix that will rotate each light proportional to the amount of time elapsed between frames by using the frameinfo.frameTime variable. Then, we simply need to update the game object's translation to equal the rotation matrix times the previous translation value. You should also try animating other properties of a point light, such as its intensity or color. Finally, it is probably a good idea to add in an assertion that the point light game objects in the scene haven't exceeded the limit specified by the max lights constant. This way, if you do accidentally exceed this limit, you will at least receive an informative error message. Now, if you build and run the code, you should see a moving ring of lights. Anyway, that's it for today. Thank you for watching and keep on coding. Cheers!